So in this installment, we're going to look at the work kinetic energy theorem. In our definition, it's the net work done on an object or to an object that is equal to the change in kinetic energy of the object. So the net work done is equal to the change in kinetic energy of the object. So the work done equals the kinetic energy, change in kinetic energy of the object. So the work done by the subject. So in looking at this, let's consider an object experiencing a constant force at rest. So we have our ground laid out with a little tree there. And so we have an object at time zero. So we have time zero. At this point, that's where the object is. And it's while at rest. So while at rest means V0 is 0. A force, a constant force. And that constant force, F net equals MA. If the force is constant, it's the same object, so the mass is constant, the acceleration will be constant. So that's what's critical here, is the acceleration is constant. So in that first increment of time, it will travel a certain distance. Let's say it travels 1 unit. And since the displacement is 1/2 AT squared, whatever that acceleration is, it's going to be related to the time squared. So if in one interval of time it traveled 1 unit, in 2 intervals of time it will travel 2 units. We'll travel twice as far. So that gives us that distance. And then it will travel 4 units. And then it will travel 16 units. It's a significant difference. So about over here somewhere. So that's what's going on. This thing is speeding up. So we have our motion that's being as the result of a constant force. So let's take a look at the position time of this. So at time 0, it's at a position of 0. And we know it's behaving by this function, x equals 1/2 AT squared. So that's going to be a parabola. The things we can read off this graph are x and t. The gradient is delta x over delta t, which is the velocity. And the area is x times t, which has units of meter seconds, which is nothing useful to us. Now, when we look at the velocity, we said the velocity starts at 0. And the velocity increases at a constant rate. That's a straight line relationship. Now, from this graph, we can read velocity in time, and the slope is delta v over delta t, which is the acceleration, and the area is v times delta t, which is the displacement delta x. Meters per second times seconds gives us meters, so it's the displacement in that particular case. Now, an acceleration time graph, we can read the axes, acceleration in time. The gradient is the change in a over change in t, which is the definition of jerk. And a times delta t gives us delta v. Meters per second squared times seconds is meters per second. And so what we said initially is the acceleration is constant. It's some number, and it remains the same. Those 3 graphs are depicting the same motion. So this is what's happening in this particular situation in terms of the position, velocity, and acceleration. Now let's see how this applies to the work kinetic energy theorem. We said that the work done is equal to the kinetic energy. So we're going to derive a formula for kinetic energy. So it comes as no surprise. The definition of work is the average force times the distance. Now, since we know that the average force produced the acceleration, that is equal to ma. Average force produces an average acceleration. Now, the distance is equal to the displacement because it's in a straight line. It's in a line, one dimension. Okay? Now, when we look at acceleration, the definition of acceleration is delta v over delta t. So our m continues to carry down through. The acceleration is delta v over delta t. Well, delta v is v minus v0, and delta t is t minus t0. So the m's and delta t's remain as such. But here's the thing, v0 we said was 0, and t0 we said was 0. So if these two things are 0, they drop out, and we're left with mass equals the instantaneous velocity over the instantaneous time times the delta x. So now, we said in our velocity time graph that looked like this. We have velocity time, and the slope is the acceleration, and the area is the delta x. So if we want the delta x, we need to find the area. So looking at our formulas, we've got mass, we've got v over t, and delta x. Well, how do we find the delta x, or the area? Well, okay, so if we wanted to find the area, in this case, well, that would be the area of a triangle. And that area of a triangle is 1/2 the base, which is the time, and the height is the velocity. So we have 1/2 vt. That's the area of the triangle. But we could have reduced this triangle to a rectangle. If that is the value v, then the midpoint here is v over 2. And now we are looking at the area of a rectangle. Now that area of a rectangle is length times width. And the length in this case is the time, and the width is v over 2. So we can see that in both cases we have 1/2 vt. So both methods yield the same area. Well, if delta x is the area, then that is equal to 1/2 vt. So mv over t times 1/2 vt, combining like terms and canceling, we can see that the t's cancel, and we bring out the coefficient to the front, and that's mvv, which is mv squared. So that tells us that the work done is 1/2 mv squared. And the work kinetic energy theorem says the work done is the kinetic energy. So therefore, the work done is the kinetic energy of the object, which is 1/2 mv squared. And the assumption here is v0 equals 0. v0 equals 0. Well, what we can see is that if we go back and look at our motion along the path, there is a certain amount of kinetic energy that's gained here, and a certain amount of kinetic energy that's gained here, and here, and here. And we have a certain velocity at each one of these locations. So we've got a v, a v1, a v2, a v3, a v4. And that results in a delta v for each of those. And so that means there is a change in kinetic energy between each of those time intervals. Well, if we look at the change in kinetic energy here from 0 to 1, and we look at the change in kinetic energy from 1 to 2, and 2 to 3, and 3 to 4, we can see that the total kinetic energy, which goes from time 0 to time 4, is going to be equal to the sum of the change in kinetic energies of times from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. So in any case, the change in kinetic energy from, say, this location at time 2 to time 3, that change in kinetic energy is going to be due to the change in velocity of those two at those 2 points in time. So that leads us to a final formula, which it will give us the change in kinetic energy, which is caused not by a change in mass, but it's caused by the change in velocity at any moment in time. So we can say the total kinetic energy is the kinetic energy it has from the work done on it from a velocity of 0, and that change in kinetic energy is due to the change in velocity. Now, one of the things that's a little more complicated here is that we might say that in this diagram that the object starts at rest and increases. So we would say it has 0 kinetic energy, and it goes to this final kinetic energy at time 4. So the kinetic energy increases to time 4, and the kinetic energy started at 0. But what we're not taking into account is that the Earth is rotating on its axis, and at the equator, that turns out to be about 1,200 miles per hour. So even an object that's seemingly at rest from your frame of reference on the equator might seem to have a kinetic energy of 0. It doesn't have a kinetic energy of 0. It already has a tremendous amount of kinetic energy by virtue of the fact it's on an Earth that's rotating. So at every juncture, we can say that the change in kinetic energy is relative to our frame of reference. So in the end, we've seen the work kinetic energy theorem. We've studied an object in motion. We've derived that equation so that we can see the work done is equal to 1/2 mv squared. And at any time, the change in kinetic energy observed is equal to the change in velocity squared. And if we said our initial velocity from our reference frame is 0, then if 0, then this equation. In either case, they work to solve any kind of work and kinetic energy problem that we see.